My name is Chris Andrews. I'll be the moderator. I'm the Director of Mobility at Pratt Miller. We're a wholly owned subsidiary of Oshkosh Corporation. We do product development and technology integration on mobility and vehicles. But I'd like to have each one of our panelists here kind of say a little about them and what they do, and then we'll kind of get into some questions. I think you're really going to enjoy this. I already have in our pre-talks with these folks. So.
Yeah, thank you. I'm excited to be here. My name is Ossa Fisher. I am the president of Aurora Innovation, and we are deploying cars and trucks to drive themselves using the latest in AI breakthroughs. So excited to be here, and we've got some partnerships even on stage with NVIDIA, Volvo, Continental, and many more. So thanks for having me.
Yeah, my name is Burkhard Huhnke, very German name, but German-American. In the meantime, I live in San Francisco. I'm the CDO of Scout Motors. That is a new company built on the original brand Scout. Super exciting, fully funded by the Volkswagen Group. So that is very exciting to be here today to talk about some of the aspects we are using currently in the development phase concerning AI. So pleasure to be here. Thank you very much.
So my name is Raquel Urtasun. I'm the founder and CEO of Waabi. And what we do at Waabi is transforming the physical world with generative AI, starting with self-driving trucks. And really a pleasure to be here today and very excited about the conversation that we're going to have.
Yeah, Norm Marks from NVIDIA. So I lead our automotive enterprise business. And since Ossa said it, of course, we also have a strong partnership not only with Aurora, but also with Waabi, and doing a lot of work together with everyone on the panel. So it'll be an exciting conversation for sure.
Yeah, I feel this is a pretty pivotal year, so let's jump right in. So Ossa, if we can start with you. Absolutely. You operate in a very safety-critical industry, to say the least. Performance is paramount in AI. How does Aurora ensure your systems are reliable, verifiable, and what practices do you use in your AI-driven autonomous technology?
Yeah, thanks for bringing up the safety-critical nature of what we do. A lot of the talk about AI over the last couple of years has been with the LLM, large language models, and ChatGPT, and that's extraordinary. I don't want to diminish that at all. I think Jensen called that cloud AI. And while ChatGPT does incredible things, it generates the recipe, it doesn't cook the meal. And I think with physical AI, which is a new era that's coming in, we are, Aurora, with our trucks on the ground, on public roads, we are interacting with the real world in real time. And that just demands a different level of care than what you get from a ChatGPT output. And so we are using what we call verifiable AI. And this has the benefits of what the LLMs are doing, that these are the massive data models, and we use human-driven data to augment our models, but then we deploy guardrails. And so let me explain a little bit what that means to contextualize it. Let's take stop signs, four-way stop signs, two-way stop signs. We've got millions and millions of miles of driver data on that. But if any of you know the drivers on the road, I have a 16-year-old who just got her license, so I know this very well. Humans don't always abide by those stop signs. In fact, we often roll them. And so if we're using an AI human-like model to determine how we navigate the roads, the Aurora driver might occasionally roll a stop sign too. And for us, that would be very much out of alignment, and frankly, it's against the law. And so we supplement that model with guardrails that adhere to the rules of the road. This ensures that we won't break the law and is also really, really helpful when we're working with regulators to explain to them how we know that we'll behave safely regarding the code of conduct that we all expect from vehicles that are driving next to us.
Yeah, no, thanks very much. So Norm, after that, why don't we talk about AV1 to AV2 models and end-to-end world models? I think it's a good way to go into it next. So,
yeah, on the heels of the keynote, and hopefully many of you were there, it's certainly a hot topic for us right now. Now, if you were to ask 10 people to describe AV1.0 and AV2.0, you'd probably get 7 or 8 different answers. And I'm not going to suggest my explanation will be 100% perfect, but just a level set. When we think about AV1.0, as we describe it, think about 50 or more individual deep neural networks that are detecting certain things like detecting a vehicle, detecting the distance between us and the next vehicle, detecting a pedestrian on the curb, detecting eye gaze, whether you're looking forward. I won't name all 50, but also trained on labeled image data. So certainly very effective in the early days, and as an industry, we're all learning what it's going to take to actually get to safe self-driving. And but what we've been learning is that certainly these models we think are super effective for level 2+ and level 3, but in order to get to full level 4 and beyond, we see the opportunity really is to move to this AV2.0 model, which really I would describe simply as moving from individual DNNs and going beyond just having an ensemble of them, but actually having one very large, it turns out, end-to-end world foundation model. And some call it a VLM, some call it a multimodal LLM, but one end-to-end world foundation model. Of course, we're proud to have announced what we're releasing to the world now with Cosmos at our keynote. But you know, the difference here is, of course, trained on video data. You know, our initial models trained on 20 million plus hours of data, and all of our customers who will be leveraging the platform, some of which are up here, will be able to then use their own data to then further fine-tune it. But if I, you know, to a layperson, a simple way to think about the big distinction is that in AV 1.0, you're detecting a pedestrian and then acting based on what you see, versus in an AV 2.0 world foundation model, that foundation model is actually predicting the next frame. So it's predicting, will that pedestrian step off the curb, or do we expect that pedestrian will stay on the curb? Will that vehicle cut over in front of us, or will it stay in its lane? So the power of going from detecting to predicting, we believe will go a very long way. So huge transformation underway. From a scale standpoint, AV 1.0 is a massive computational challenge. You know, a 50-car fleet collecting data is about 2 petabytes a day. But the data for AV 2.0, we're talking order of magnitudes of 50 to even 30 times larger. So significant challenge, and happy to be a part of helping the industry forward along the way.
Yeah, I mean, this is exciting stuff. So, Raquel, can you tell us, now that we've gone into end-to-end world models, how your team is pioneering safety and how you're using them?
Yeah, so now that we went from 1.0, I guess, to 2.0 as we continue on the discussion. Yeah, so Waabi, you know, is pioneering foundational models that can use multiple sensors, including LiDAR, cameras, radar, etc. And the way to think about our models is that you cannot just take, you know, an LLM or a BLM and say, you know, go and, you know, drive vehicles, right? That's not going to be safe. So there is a few things that you need to do, and very different architectures that you need to you know, develop in order to have something that has 3 characteristics. Is able to be super efficient, so that you can actually run it on the vehicles, as Norm was saying, with very little compute. Is able to generalize to the unknown. This is something that, you know, LLMs are amazing at you know, doing natural language, right? Are amazing at answering questions, interfacing with humans, but oftentimes memorize. If you go a little bit out of distribution, right, they don't work very well. So we need to build technology that has that generalization property, you know, in nature. And the third bit is that for a safety critical application like self-driving, you need it to be provably safe. Being safe is not enough. You should be able to verify and validate the system, and that's what you get with you know, Waabi's technology, which is very differentiated with other 2.0, where you get the best of both worlds. You get the ability to verify, but you get the end-to-end power of next generation, you know, generative AI. And last bit I will say is that in order to beat the scaling laws, the thing that these systems have to do is reasoning. Right, and we saw that on Jensen's keynote, right, is that you start with, you know, pre-training, which is what you were talking about, then you fine-tune. Well, next generation is reasoning, and that's what we really have been doing over the last 3.5 years at Waabi, is build AI systems that are end-to-end, but are able to reason in a very, very effective manner, so that the system can understand the consequences of its actions, can really decide you know, all the possibilities that are possible, right, and decide what is the safest maneuver at every point in time in a fraction of a second.
Wow, that's incredible. Thank you.
So eloquent, right?
Yeah, it really is. I think you guys were talking about how there is it's not a natural transition, but it's a break in a whole new way of doing things. And I think that's what a lot of people need to get their arms around. It certainly took me a little while, but it's eye-opening. So Dr. Burkhard, you want to tell us, we've talked about AV, but are there other product development things? Tell us a little more about that.
Yeah, let me take you away for a minute from the exciting topic AV and explain you how we are using AI in the development process. We talk about the digital twins, as everyone knows, as a very interesting fashion word, but what does it mean? It's actually a replica of the physical surrounding by creating a digital twin of your existing physics systems. If you do that, and that's what we've done at Scout Motors from the beginning on, because that has huge opportunities, and it's actually a digital revolution which is ongoing there, from my perspective. If you think about the physics and the science behind the car, it's all about a differential equation solution. So if you think about traditional CFD, which is computational fluid dynamics simulation, how you would do aerodynamics in the past, now you have the AI. You can run machine learning, and you optimize your system with GPU power and optimized methods very quickly. So that allows you actually to use physical prototypes very early in the phase. Now you can go through every physics of the car besides fluid dynamics, besides aerodynamics. You can go into the structure of the car itself. That's a safety structure. You can optimize the materials, you can optimize the structure. You can learn from previous tests, crash tests, and build that into your modeling. So you have instantly a feedback loop closed with the real-life data which you have to feed in. In example, for the wind tunnel testing, you need sensors to feed in the data and feed the model with AI and ML data to make it better and more precise. So you're receiving, in the meantime, an accuracy of 99%, which is ridiculous high. Now you can imagine, we're not replacing the designer. So Chris Benjamin, if you're here, our beautiful Scout Motors design hasn't been designed by AI and will never. So, but it's something in between science and arts. And how can we expedite the process behind the development and engineering of these beautiful A-surfaces and optimize the underlying structure to be weight optimized, structural optimized, safety optimized, thermal optimized, and so on. So I think we are leading these kind of efforts within the Scout Motors organization. We have done very successfully reduction from iteration loops from 24 hours down to 5 seconds in the underbody airflow optimization. Now we are tackling the safety relevant components on the crash test dynamic, and of course that's ongoing in every physics of the car. Durability testing, fatigue analysis, everything is now coming into this world by adding AI and machine learning, and that is just great. So back to you, Chris.
Yeah, I mean, that from 24 hours to 5 seconds. This is what CES is about, right? So this is, I think this is a pivotal year. So anyway, Ossa, can you tell us how you're using all of this technology to help in the safety of your real world scenarios?
Yeah, and I want to build on what Burkhard said. Simulation is critical to what we do, and echoing Jensen from his keynote, there's the learning model that's continually ingesting data and refining what it's doing, and then for us in the physical world, there's obviously the compute that exists on the truck and is navigating real world situations, and in that middle is the digital twin, which Burkhard referenced as well. And so simulation is core to how we're developing the Aurora Driver, but we've been on this journey for a number of years, and we've learned a few things. So simulation in and of itself is not actually a test, right? You actually have to be able to grade the simulation. And when you're talking about billions upon billions of simulations, how do you know which ones are passing and which ones aren't? And so one of the latest developments at Aurora is we're using AI to grade the test, because no human, and go back 15 years, humans were grading the simulations. Now we can use AI to grade the simulations, but we see simulation as an and, not an or. We couple simulation with real world experience experience on the road. We're on the road in Texas every day to navigate the more mundane lane changes, stop signs that I referenced earlier. But we also do track testing. And just to put this into perspective, why would you need track testing in addition to simulation and real-world driving? We'll take a blown tire, for example, right? We can simulate that, but what we really need is that the hardware components are integrated with the software components, seeing and responding correctly. So on a test track, we can blow out the tire and verify that the simulation actually did respond, it was appropriate, and that the truck itself also sees and responds appropriately. One other way we use a test track is we were running simulations, and odd, but you see this more than you would think, motorcycles going at 80 to 100 miles per hour in between lanes on freeways. The simulations seem to be catching it, but when we're in the real world, our safety drivers are saying, we're not sure we're seeing that far enough in advance. And so we went to the test track and actually hired a stunt driver, pretty incredible, who started at 10 miles an hour and then built up to 100 miles an hour to confirm that the perception system was in fact working accurately and that our motion planning system, which is responding to that actor, was also doing it correctly. So we see these all working in synergy and that simulation is a fundamental piece of that.
Yeah, that's amazing. And the simulation and the models are only good when they're validated, right? And then,
Correct, yeah.
And then the system gets a lot more information and it gets better overall. Yeah, that's amazing. Raquel, we know we've talked about safety and how critical it is. Tell us how you're using simulation in similar or dissimilar ways. So.
Yeah, great segue, I guess, to what Ossa was saying. So we are a simulation-first company. So what does it mean is that in the area of AI, in the area of generative AI, data is extremely important, as Norm was saying. And what we can do with neural simulators is really get to a level of fidelity that has never been seen before. And what is great with simulation is that you don't need to wait for nature to show you things. You can actually create all those simulations. And more importantly, since our neural simulator is an AI system and the software stack is another AI system, they can actually play games. And the particular game that is very interesting is the one where they play adversary. What does that mean is that the simulator is trying to create tasks that are very difficult to handle for the software stack, right, for the virtual driver, so that every data point is extremely informative. Why is this important? Because suddenly you can actually train the systems at a tiny fraction of the cost that otherwise you will. So it's not anymore about billions of simulations, it's really about which simulation is more informative. The other thing that is, when you talk about simulation that is important is that, well, simulation by itself, sounds cool, but, is not sufficient, right? As Ossa is saying, unless there is one key thing that you need to do, which is if you can prove that your simulator, like driving with the same software, the entire software stack on simulation is the same as driving in the real world, then suddenly you actually have that ultimate driving test, because on the cloud, at the scale, you can expose the system to all the different scenarios, situations, etc. And that's what what we build at Waabi with Waabi World, really pushing that neural simulator to the next level. And it's been an incredible accelerator to make us super capital efficient and requiring driving in the physical world only for validation of the system versus just general development. So it's been an incredible thing, and I think as we go into the physical AI year of 2025 and beyond, we are going to see more and more neural simulators really take over the world.
It's exciting, and it's kind of like the tools you're having in your toolbox are much more powerful now, right? And I think we're just going to find out a lot more things that we're able to do moving forward, right? So. Norm, to you, we've talked about AI and autonomy and development and digital twins. Does it have any bearing in other robotics or AMRs or manufacturing inspections or other places?
Sure, I'll come on to that, but if you don't mind, before I do, just a couple comments about what Ossa and Raquel were talking about.
Please.
One of the beauties of these foundation models too, and you were alluding to this, but just to put a finer point on it, is that they can be useful not just for training the actual self-driving software, but actually being used to create the controllable scenarios against which you would then run a simulation. So just to build on that, to try and make sure the point is clear, these foundation models can literally take just 9 frames of data and then build out the rest of a driving scene. And complete the rest of what you would expect would happen. But then, and you were referring to this when you said a neural simulator, when you apply what's called neural reconstruction, the field of AI, we take this now snippet that we have, and now we recreate it in potentially thousands of different scenarios. So a drive that might have been in the day in a neighborhood could start out the different times of day, to sunrise, to sunset, to the different environmental conditions, rain, snow, wind, to even taking that drive and actually having it turn into a drive on the highway. And this gives us so much promise to create the millions of scenarios that we need to test for, to ensure that we also test for all these rare and dangerous corner cases. So there's just so much promise here, and we've got some real leaders who are doing great work in the space. So I think the question was AI to manufacturing or robotics.
Yeah, that's extremely important. I think this is the key to what we're talking about here today. So thanks for adding to that and clarifying it. But yeah, in other forms of AMRs or other robotic areas, we've talked about on-road things here, but this technology can be used in many places and is used in many places. So manufacturing inspection, manufacturing in general, other robotics.
Yeah, let me speak to that. Now, probably the easiest place to start is an AGR AMV is effectively very, very similar to training an autonomous vehicle. A robot that's going to transport parts around in a factory needs to be able to see what machines are in the factory, the proper path to take. And so this is actually quite similar to autonomous vehicles. But humanoids are a whole nother level of complexity. Being able to train a humanoid robot to complete tasks that we do that are extremely precise. Obviously, autonomous vehicles have to be extremely precise. But a humanoid robot has to be able to pick and place things at such a level of precision and accuracy that the complexity of this is extremely difficult. And again, another place where these foundation models can be used to run through all the various different conditions. And so now imagine I have a humanoid robot. It's actually picking a part off. It's putting it into a bin for a good part or a bin for a bad part. And then you alluded to this, now I have AI-driven inspection that's actually viewing the part to determine, did the robot actually do that task properly or not? Did it potentially place a part that was defective into the green box, not the red box, to oversimplify it? And so that's the power of the AI. So camera-based inspection, not just human-based inspection, which has improvements in the efficiency, the accuracy of the quality, but also it'll speed up throughput too. So AI can be used for this as well, probably sounding like a broken record. As you might imagine, a foundation model can help train all the various different combinations that you might see. So terrific opportunities there. And then a final comment, just building on some of the earlier comments that he made. GPU accelerating a CAE or a CFD workload is super important. And in the space that we're going to with electric vehicles, the coefficient of drag to be able to get the most out of a battery is hugely important. And so what we're seeing many of our customers move to, and it was a small part of the keynote, but one part of the announcement we also made is a blueprint that we're doing in this space where you can actually take physics-based AI and run it in a digital twin with, nines, if you will, levels of accuracy that approximate the same level of accuracy you get with CAE and CFD, but in real time. Imagine seeing the coefficient of drag and moving it around on a part and seeing the various different combinations and iterating on the design. And literally, you think, is it 24 hours to 5 seconds? Okay, but now we're potentially taking months out of the design cycle because we're iterating at high levels of accuracy. You still will put it through the final CAE and CFD to have 100% accuracy, but you can make many, many changes along the way that normally it literally takes months out of the process.
I'd love to build on that because I think this world of physical AI requires physics AI. And if you think about self-driving, everything from inertia to gravity to wind speed are critical. And so for the AI to be able to generate that, opens up a whole new era of speed for the industry. And I think we're just at the beginning of seeing the potential of physics AI.
Now, this is exciting. And the more data you feed these models, the better they get, right? So having critical information is going to be great too. These are going to get stronger and stronger, and the tool's going to get stronger. So Burkhard, on that, why don't you tell us a little bit about how you're doing exactly what was just talked about?
Oh, actually, we're doing it.
Yeah, that's what I mean.
Yeah, let's hear it.
Scout Motors, actually, normally we should talk. You wouldn't believe that. It's actually working. So a digital wind tunnel, to do a digital release is, of course, the vision, right? That instant information from iteration loop of the spoiler optimization allows you an instant iteration loop to optimize. Yeah, that is just aerodynamics, but the structural optimization, going into the virtual prototyping phase, replacing physical prototypes, which costs you $1 million per prototype. Not just talking about compressing the timeline of the development process, probably not every time necessary, but the release of every car, and if it's just software and functionality, this has to be tested with these new modern AI models. Because with the lessons learned, as everyone knows from the personal life, with your experience, you do different decisions. So how do you train also this process of, let's say, software release with lessons learned and information that you're not launching cars with software bugs anymore. So it's a lot of potential. We use it back to the Scout Motors world in regards to aerodynamics and structural analysis in the fatigue analysis. So we are expecting a digital release before we have the physical release. And that's replacing a lot of very expensive iteration loops through physical testing. We'll always have to prove, because the customer is not driving models, digital models, the customer is going to drive beautiful cars, but to get to the point to release that in a very reliable and robust way, that is the toolbox we are using very successfully already. Yeah. And again, back to the timing, I think 24 hours, that was when we started with that simulation. Now we had 5 seconds after 12 months. Now talking with you about the right GPU power, this is instant information you can get.
Yeah, it's exciting. I know we've talked about, I've talked with many others, including yourselves, that these tools now, sometimes, not always, that first digital twin model can actually be extremely close to the first drivable model. I've heard people that are, within a few percentiles of driver dynamics, feel, aerodynamics, even in the virtual world. Doesn't always happen, but the stronger these tools get, the more that will happen. Was there something you want to add?
I just had to say, as an enthusiast who's been in automotive my whole life, and by the way, that if anyone is in the audience that knows me well, likes to drive quite fast, probably shouldn't say that out loud. But the other thing that's super exciting to me on a personal and professional level with the virtual wind tunnel, which is exactly the right way to describe it. Imagine the future of Formula One and Formula E. Where they have so many regulations on what they're able to test and not test, but to be able to apply this physics-based AI and be able to iterate, not in race, mind you, but post-race, to be able to learn from it and test out the various different combinations of the angle of the vehicle. This is going to be really fun to watch.
So I can say from a Pratt Miller perspective, being in motorsports, that is already very exciting. In driver-the-loop simulators, being able to drive these things, development of a new car. One of the people I mentioned was one of our teams, and they got to the track and drove the car for the first time, and it was within 2-3% of what it was supposed to be. So it really is amazing tools, and they're only going to get stronger. So yeah.
Yeah. So if I can add something to this, I great conversation, and definitely all in on what you guys are saying. But I think one thing that we haven't talked about that is very exciting is that it's obvious digital twins are extremely important and have enabled, as you were saying, massive unlocks for folks like yourself. But what is very, even kind of the next level now that we are seeing is that these digital twins were built by humans before, where you have, humans, artists creating, super detailed CAD models, etc., that then you use to, learn, to run the simulations and use that training data to then do simulations. So the bottleneck was on the creation of the content. What is really exciting now is that we can create that content also automatically. And then suddenly you have the, the next generation of unlock, which is all those simulations are grounded in reality. And, we see so many things, when we drive, we do, commercial runs in Texas, in a daily basis. Every time that you go on the road, you see thousands and thousands of vehicles. So we can clone everything automatically. And then that's automatically part of the simulator. So this really enables you to go to the next level of scale and with a level of realism that is unprecedented. And I think that is really, really exciting. And, not only for automotive, but all the applications beyond that is really going to revolutionize, the world.
Well said.
No, that's great. And I think we've got a little time left, but I'd like you all to give us kind of your summary of past, present, future in artificial intelligence and just general technology advancements. And, the interesting part about this is it's not technology for technology's sake. This is really making a difference in people's lives and safety and a lot of other things. So if each one of you could give us a little bit of your perspective, where we've been, where we're going, and what to expect.
Sure, I'll start and we'll go down the line. I think hopefully if there's one thing that's clear either from this panel or from this week is that all the big boulders that previously prevented physical AI from manifesting in the real world, they've all been knocked down. This is real. This is now. We're launching this year and ready to do so. And it's on the backbone of decades of AI work, but it goes all the way back to the very first microchip from the 1950s. And so the history that got us here, we're standing on the shoulders of giants. It's an overused phrase, but it's so true. And this era looking forward is one of the most exciting in our lifetime. And so I'm honored to be on the stage with this community, and I just know the next several years are going to blow all of our minds.
Yeah, thank you. Yeah, different approach probably from the customer's perspective, product perspective. This is an opportunity which provides us a toolbox to deliver exactly what we envisioned at the beginning in regards to functionality and features and the capability of the product we are delivering. And this toolbox is helping us to understand better the precision and also the robustness of the product we are going to deliver. So what the customer wants can be understood very early in the phase. For me, it's a shift left in the development process, which is going to be a revolution. You understand very well how to make the right decisions at the beginning, correct probably decisions basically on an instant feedback loop from these ML-driven models, and that is a game changer, and I love to be part of that.
So as an AI scientist that has been doing this for 25 years, I fell in love with this idea of an artificial brain, 25 years ago. So yes, I'm pretty old. And
you look great.
Anyways, I try to, yeah, whatever. Yeah, so it was this idea, right, that was fascinating, like an artificial brain that can do tasks that humans can do. And there was a lot of research that was needed because the algorithms at the time were cool kind of prototypes, but there was nothing that you can really bring to the real world and see what, what we are seeing today. So the, kind of the acceleration, massive acceleration, and what we are seeing today as an AI scientist has been amazing to see. You cannot imagine what this has been personally. Now, as it relates to what we are doing at Waabi, so we are launching driverless this year. So you will see our trucks with no human. I'm not talking about a demo. I'm talking about really something that you can commercialize. So it's great what we see ahead of us, and trucks is really the first use case, and we are not going to stop there. Whether it's robotaxis, humanoids, as Norm you mentioned before, as a very exciting use case, warehouse robotics, you name it. The moment for physical AI is here, and stay tuned because the physical world is about to change massively and unlock so many good things for humanity.
Well, first of all, happy to hear that all of us actually are saying it's about physical AI, and that really is the path that we're on. I can't help myself. I'm not as smart as Raquel, so I didn't imagine artificial intelligence 25 years ago, but I will tell you, I was smart enough 7 years ago to come to NVIDIA where I knew the future of artificial intelligence was going to be.
You were smarter than me on that,
I'll leave maybe just one example, pairing artificial intelligence to digital twins, and in this automotive context that I believe, by the way, there is some early work being done. Can't name who's doing it yet, but imagine, we've talked about the power of AI, but imagine having a digital twin of literally every single vehicle that's on the road, and monitoring the digital twin of that and identifying that maybe we have a fault in the vehicle, maybe we have something as simple as Apple updated today and now it's not working effectively in the vehicle, or any number of even, even quality faults in the vehicle. The power of AI is you can test the various combinations of how to solve for that problem, and if software, for example, and oftentimes it can solve it, you can actually test whether the software has solved it in the digital twin of the vehicle first. And when you know that you've actually solved the problem in the digital twin, now you actually pass that on to every one of the vehicles that are experiencing that same problem. Or as simple as that triggers, now we know the software update will be effective and it will work. So just one simple example, but one that I think is going to be very powerful for us in the future of autonomous vehicles on the road. So that power of AI interacting with digital twins and real-time digital twins, and whether it's a vehicle on the road, a warehouse that's operating, and being able to identify a robot actually has to traverse boxes that fell off and it's got to move around. So many examples here.
Yeah, I mean, this is exciting, and this is why we all come to CES, and to hear what we just heard from this panel, it's inspiring to me. And as I'm sitting here hearing you talking, we only got a few minutes left, but I'll throw one last piece out here that I think takes us to a whole nother level, right? We talk about simulation, foundation models, world models. We're now able to take the physical world and utilize it in a way we haven't been able to before. What I heard just now, too, that got me thinking is, where else will this lead? The fact that we can come out with predictive models that have a high degree of confidence, more than probably ever before, especially in the physical world, and to maybe find a way to work in that physical world model, like you said, with wind tunnels, and be able to change or see what the wind is going to do or what the motorcycle coming around you may or may not do. That's a whole nother level. And will that also lead to how we develop our new designs for transportation systems and roads and cities and all that? So I think it really has a lot more power to change lives and improve lives for the average person, for persons with disabilities. There's a lot here that I think that it is very exciting. A couple more minutes if anybody wants to comment on that, but
I couldn't agree more. We're in a new era where almost anything that's capital intensive will undergo fundamental change, from an investment cycle, from time to market. The speed of innovation is exponential at this point. So it's hard to predict what's 5 years from now, but I can imagine even this room would get built very differently 5 years from now. Yeah.
I think Raquel may know what's going on 20 years from now.
And I'll bet on it too. Whatever you say, Raquel, I'm in.
Well, with that, I'd like to thank everybody here. Thank you so much. This has been life-changing for me, getting to meet you and hearing about all this. And thanks everybody here. And we appreciate you coming here and sitting and listening to us. And have a great CES.
Thank you.
Thanks.